Uranus isn't just a flat-out planetary nonconformist. It is also a total exploration mystery. No wonder, after all, the gleaming blue ice monster was only visited by Voyager 2 and studied up close and properly. The data is scanty. In spite of this, scientists have now succeeded in uncovering a number of Uranus qualities that are as astonishing as they are befuddling. The planet actually orbits the Sun on its side. Its magnetic field has not only 2, but 4 poles, and its surface is a chilly -216 degrees colder than it should really be. Now, however, space experts have finally managed to reveal a little more insight into the darkness of Uranus, and its abnormal 4-pole magnetic field likely goes back to a striking event hidden somewhere inside the heavenly body. The Uranus family has grown since it was just a couple of months ago that scientists reported they had identified a previously obscure moon in the domains of the far-off ice giant. In like manner, the number of Uranus moons increased from 27 to 28. As befits a lunar child, the newfound satellite is also the smallest of any of Uranus' moons found to date, designated with a temporary name, S223U1. It's only 8 kilometers across. However, the greater question marks that have been swirling around Uranus for so many years are more of a reason to be curious. As already mentioned, this is primarily because the most cutting-edge information available to us about this strange ice world still dates from 1986. Although the data gathered by Voyager 2 might seem a bit outdated, it's still good for new surprises. Specifically, the Voyager data revealed a strikingly strong radiation belt, filled with vigorous, fast electrons in the planet's magnetosphere. The intensity of the particle flows was even similar to that in the outer magnetosphere of Jupiter. However, interestingly, unlike the king of our solar system, there was hardly any plasma in the domains of Uranus from which the electrons might have originated. This seemed all the more puzzling, given that the 5 largest Uranian moons should have been constantly releasing water particles into space, which would then be ionized by the magnetosphere of the ice moon. Thus, for many years, scientists struggled with the Voyager data, and only recently have they managed to provide an explanation for these unusual conditions. As a matter of fact, the key to the galactic mystery was also hidden in the old data, but the researchers had simply overlooked it until now. This only changed when the team led by Jamie Jean-Sky from NASA's Jet Propulsion Laboratory re-examined the data. Voyager 2 had also studied the radiation and particle density in space long before and after its flyby of Uranus. However, a strong solar storm had occurred shortly before the probe's arrival. This packed the magnetic field of Uranus and tore the surrounding plasma out into space with it. And while this event robbed the magnetosphere, the solar storm filled the planet's radiation belt with high-energy electrons. Essentially, Voyager 2 had arrived at the wrong time and did not examine the planet in its typical state, but in a completely unusual circumstance. Scientists say that the planet's magnetosphere would have looked entirely different if the spacecraft had arrived just a few days earlier. In a way, Voyager 2 had perfect timing, as such extreme conditions are likely to occur only around 4% of the time. While there is no doubt that interpreting this nearly 40-year-old plasma mystery marks a significant transitional step in Uranus research, there is also no question that the ice monster's fascinating magnetic field continues to present us with serious challenges. But how is a planet's magnetic field shaped in the first place? Well, in the case of our home planet, which is known to have a normal dipole magnetic field, this is created by convection flows in the fluid outer core, which act in combination with the solid iron core as a geodynamo. However, this so-called dipole field, which has 2 opposite poles, requires a certain minimum thickness of the convective layer. This doesn't seem to be the case with Uranus, and the scientists' models show that a non-dipole magnetic field can be produced. At the point when the flows capable are restricted to a thin layer somewhat far out, moreover, we know that the inside of the ice giant is made out of a solid core on one side and a blend of water, ice, ammonia, and methane on the other, which is possibly conductive. Furthermore, thusly, a contender for a convective magnet dynamo. What we don't know, anyway, is what the lower layers of Uranus seem to be and what could obstruct the flows at these planetary depths. One hypothesis depends on the understanding that the water there is expected to be in a colorful superionic state, which amounts to nothing more than that the oxygen atoms of the water molecule structure a solid cross-section in which the hydrogen particles can move around freely. Then again, there is a hypothesis that likely relates to the most stunning dream of every diamond setter. It could even be pouring diamonds inside Uranus. The reality that the inside of the ice giant may exemplify a planetary diamond is once again because of the pressure and temperature, which are presumably adequate to break down hydrocarbons and pack the carbon into precious diamond gems. In the same breath, this diamond stone downpour could also make sense of why the planet has a multipolar magnetic field. After all, the diamonds, along with nerve gas and ice, move into the depths, which ultimately causes convection flows in the mantle since conductive particles are also generated in the process. These would also contribute to the unusual Uranian magnetic field. So far, so possible. But then, another series of research studies has now concluded that the magnetic field's secret actually has a completely unique foundation. In this case, we are dealing neither with the impacts of superionic water nor with the outcomes of the diamond downpour, but with the aftereffect of non-mixable layers in the planet's interior. The answer to the magnetic field mystery lies in the way that the conversation about the magnetic field is now enhanced by a third methodology. This is thanks to Burkhard Militzer from the University of California in Berkeley. Exhaustively, the renowned scientist used some high-resolution virtual simulations that recreated the behavior of methane, water ice, and ammonia under the conditions inside Uranus. What was exceptional about this was the fact that, due to an adaptable calculation, Militzer was able to mimic the processes with nuclear accuracy for the first time, with an amazing outcome. When the professor of Earth and planetary science checked the model out, the water had separated from the carbon and nitrogen. As a result, a few layers were made that can't blend in with each other. At the very top is a conductive layer of water and ammonia about 8,000 kilometers thick, which is probably somewhat fluid. This is also the region where the convective flows happen, which act as the driving force of the multipolar magnetic field. Just beneath that, there is a similarly thick zone of nitrogen-containing hydrocarbons whose hydrogen content decreases with increasing depth and pressure, eventually resulting in a few layers of these compounds that become increasingly denser. According to Militzer, this situation prevents vertical flow, which is why these layers can't play a huge role in the formation of Uranus' magnetic field. As such, the hidden interior of the planet acts like oil and water, and most importantly, the division into two emissive layers can explain why Uranus has such an interesting magnetic field. But with no guarantees, as so often the case, the hypothesis still needs to be put to the test through future investigations. This could be done, for example, with lab tests under high pressure or, in the best-case scenario, through a direct close-up investigation. The sobering future of the Uranus missions, unfortunately, is that there is currently no program that has reached an advanced transformative phase and would go beyond the status of an unclear idea. One of these ideas goes by the name Inus and includes two individual probes, one of which flies to Uranus and the other to Neptune. If the project launched by the ESA is indeed realized, the divisible probe could advance into the vast expanses of space in just shy of 10 years. Whether and when this mission will ultimately be realized, however, is currently written in the stars, and with it, all the answers to the Uranus questions that are still unanswered. As briefly mentioned at the start, the ice giant is tilted at almost 90 degrees, and its rotational axis is thus in stark contrast to those of the wide range of other planets in the solar system. On a basic level, scientists expect that the celestial body was tipped on its side by a huge impact, but exactly how this violent event unfolded and what it meant for Uranus in the period that followed is still a mysterious problem. A simulation had shown that the ice giant might have collided with a protoplanet twice the size of Earth around 4 billion years ago, and since the larger-than-life crash partner heaved ice and rock into the center of Uranus, this event is sometimes used to explain the planet's multipolar magnetic field. However, this also applies to the puzzling rapidity of the celestial body. Despite the fact that Uranus is not the outermost planet in the solar system, it is the coldest of all, with a base temperature of -224 degrees Celsius. In this regard, the impact could have stored huge amounts of ice in the outer layers of Uranus' mantle, significantly affecting the planet's heat flow.